inside these equations in here to get the second value of it. So as we can see from here, how many times you need to iterate to find and somehow the clear answer? You need about 10 times. Why we say that? Since last week we are saying that is Newton-Raphson is more efficient because this polynomial it possesses multiple roots. It has a multiple roots. That's why is the standard Newton-Raphson. It will be taking more iterations, is about 10 or 11 iterations to find the answer. So now let's solve this one just only using the modified Newton-Raphson. So we are going to use this equation in here. Okay. So using this equation here at the first time, okay, our initial value of x is going to be equal to 0. So of course is our true value is equal to 1. So the error is going to be equal to 100. So I am using this 0 inside this function, but I need also to find the first derivative and the second derivative also for the function to put all the values inside the modified Newton-Raphson. So I will go for the next value. So xi plus 1 for the next here, it's going to be equal to 1.10526. So true value minus the result over the true value. So I will get the error is equal to 11%. So now again, I'm going to use this value inside my function here, and also the first derivative and the second derivative to find a new value of xi plus 1. So the answer is 1.0. I find the error. The error is 0.31. You will repeat again for the third iteration. So you can see here, it's the answer is equal to 1. So the error is going to be really less. So it's 0.00024. You iterate one more time for more decimal points. So till you are going to get the answer is equal to 0. So this is the true value. True value is equal to 1, and your answer here is equal to 1. Okay. What I want you to do here, this is the exercise, and this is your function. What I want you to do, I don't want you to use the standard Newton-Raphson. I just only want you to use the modified Newton-Raphson to find the roots of the polynomials. Okay. You need to iterate till the error relative is less than 0.05. Your first time you are going to use x is equal to 0, and the second time you are going to use the x is equal to 0.2. Just only do it for x is equal to 0 first time, and try to get the error it's less than 0.05. The answer you can see it here. Okay, this is your first iteration, and this is your second iterations. Okay, I don't want you to do it all because you are going to iterate about 5 times. Just only make it for second or third iterations only, and compare your answer inside the PowerPoint files. Okay, just try it. I'm going to give you about like 5 minutes. If you have any questions also you can ask. Don't go for the second one. Don't go for x is equal to, just only solve it when the initial value x is equal to 0. Try to get the same exact values. If you have any questions, please ask. Take your time, 5 minutes. Okay, I hope you are getting same values, even for one iteration, two iteration. Is it okay?
Okay.
Okay. So let's move to the second topic for today. And this is an important topic. We are going to talk about the system of non-linear equation. So what we had learned just all the time from the starting from finding the roots of the equations, bracketing methods, or also we are using the open methods. We just only talking about the linear equations, which is having just only one unknown. So we are talking about, let's say, finding the roots of the equations of the function. It has one unknown of x. So the linear equations, it could become in a form of function 1 and function 2, and it has just only one unknown x. It can be solved in this form. The function is equal to the constant value of a1 with the x1, a2, x2, so on till an as a constant and xn minus a constant value of b, and we need to make them to be equal to 0. Today we want to talk about the non-linear equation. So these equations of linear is going to give you a line. So how about if you're talking about the non-linear equation? Non-linear equations, it's going to be like at least you're going to have two equations. These two equations, it has two unknowns. As you can see from here, we are having x and we are having y. Also goes for the second equation, it has an x, it has an y, and also it has an x. So this is what we call, this one is non-linear equations. And the curve for this and these types of equations, they are not going to give you a straight line. They are. So in our case in here, we were using the bracketing methods, or also we are using the open methods to solve for a linear equations. How about this type of equation, nonlinear equations? How we can solve these two equations together? The first things that you need to know about nonlinear equation, when you are going to solve to find what's the value of x and what's the value of y that make this function is equal to 0, that you need to solve the first equation and the second equation together at the same time. You cannot just simply say, I'm going to take the first equation, I'm going to try to solve it, whatever you want, then I will find what's x and what's y. Then I will go for the second equation by itself, I'm going to solve it, and I will find the value of x and the value of y. If you did that, you will find that this value of x is not going to be equal to this value of x. And this y is not going to be equal to y. So that's why for the nonlinear equation, we need to solve equation number 1 and equation number 2, all of them at the same time. Okay. So before we start to do this, or how to solve, like for our example here, we need to solve that using the expression. So we want to make these equations in a form of a function. So that means we need to rearrange. So we put it in a form of a function. That function, you can give it whatever you want, u and v, or f or y, whatever. So here is giving the function u, which is having two unknowns, x and y, is equal to x squared plus xy minus 10 is equal to 0. And the second function, rearrange, put the 75 inside. So y is equal to 3xy squared minus 57 is equal to 0. So now I have these two functions. I need to solve them together to find what's x, what's y, that make my function is equal to 0 for both. Okay, so the two methods we are going to use to solve ask questions. Fixed point iteration. What is this methods and what we need to do? fixed point iterations to solve for the first equation and the second equation. What we need to do? This is from the last week.
Rearrange the equation. Try to written it.
Okay, what is it? What we need for fixed?
Rearrange the functions first.
Exactly. Thank you very much. This is what we need to do. We are saying that is the fixed point methods. It's the easiest methods. What we need to do, rearrange the function. Last week we are talking about, because we are having linear equations, so we are having one unknown, right? We are having x. So what we are saying, we rearrange by putting x into the left side of the equation, right? But this time I'm having x and I'm having y. So it's up to you. Maybe the first equation I'm going to rearrange based on this x. I'm going to take this x to put it on the left side, and I take y, and the second equation I'm going to rearrange it for. So I will put it here. Okay. So for the fixed point, point iterations, I need to rearrange. So first equation, rearrange for x. Second equation, you need to rearrange it for y. Okay. So is it clear how to do the fixed point for the nonlinear equation? Any question? Clear?
Clear for me.
Okay, so it doesn't mean that you have to arrange the first equation for x and y is for the second equation. It's up to you. Maybe you want to rearrange the first equation for y. Maybe you want to arrange, and the second equation you need to arrange it for x. It's up to you. But it's logically is we know that it's x, y, the order of the alphabet. Okay, so first we are going to rearrange the first equation for x and the second equation of y. Okay, I think still most of you remember that it's fixed point iteration. We need to see how is our values, because this is an open methods. And the disadvantage of the open methods that it could diverge, right? If the fixed point is diverge when you are arranging x and y, and you can see the error is start to increase or the values start to be looks weird, what you need to do to solve that? If the fixed point methods start to give you diverge values, what you need to do?
Choose another method.
I use another methods because asking you to use, you cannot change the values, you cannot choose another methods. Your sound is really weak. What is it?
side of equation.
No. Yes, this is the answer. If you find your first time you are rearranging this equation, let's say that it's you arrange first time based on this x, and you arrange the second equation based on this y. Then you start to calculate x I plus 1 and yi plus 1. So you start to have the values. So you are looking at those values looks really weird. So something wrong. So what you need to do, cancel this method and try to rearrange. Maybe you are going to arrange based on this x, and maybe you are going to rearrange based on this y. Okay, this is how to solve the divergence of the fixed point methods. Okay, so let's see the example. I'm going to solve it to you, and after that you are going to solve the exercise. Okay, look at my Excel file here. Okay, okay, our initial value, we need here to determine the roots using the fixed point iterations with initial value of x 1.5. So x here is 1.5, and initial value of y is 3.5. So I have these two nonlinear equation. So the first one is x squared plus xy minus 10 is equal to 0. And the second function is y is equal to 3xy squared minus 57 is equal to 0. So the first equation of the function u, I'm getting this x. So when I arrange for this x, so this is I'm going to get 10 minus x squared over y. And the second equation, I'm going to rearrange it based on this y here. So I'm going to get the answer of 57 minus 3xy. Okay, any questions about how to make the arrangement?
Yes, sir.
Okay, so first, when x is equal to 1.5 and y is equal to 3.5, I need to find the value of x here. So I'm going to use these two initial values into the first equation. What's the answer is going to be? Can you try with your calculator? What's the value is going to be? Okay, so when x is equal to 1.5 and y is equal to 3.5 as an initial values, and you put these values inside the first equation here, what's the answer of xi plus 1 is going to be? Can you use your calculator and tell me? The
X
answer
2.214.
exactly perfect. Okay, so now I need to find the value of y. So what's the answer is going to be?
$41.25.
The answer is going to be negative 24.37. I know what you have done, okay? The idea is, first time, you are having your initial value is 1.5 and 3.5. You use these two value, you put it here inside the equation of x, you get the value of x new, okay? Again, when you go for yi plus 1, you use 1.5 and 3.5. You use the new the old value. So that's mean when you are going to calculate for yi plus 1, is going to be 5 minus 3 times 2.21429 times 3.5. Okay, so no x no more is equal to 1.5. So forget the old value, use the old value. That's why the answer here is going to be equal to negative 24. Clear? Try.
Please, but
Okay. So the first iterations, the values looks weird. Suddenly I am from 3.5 jump to negative 24. Let's be sure. Let's go for the second iteration. I need to find now the value of xi plus 1. So xi plus 1 is going to be equal to, try.
negative 0.209 ke sir?
Negative 0.209. Perfect. So the last value of y is going to be
Hmm, 429 and 7.
T. Okay, perfect. When you are now looking at those values, is this methods or this way of arrangement, this arrangement considered is converge or diverge? You start from 1.5, then suddenly it's 2.2, then suddenly it's negative 0.2. Now it's 3.5, negative 24, then suddenly it's 429. Is it converge or diverge? This one is considered it's you are diverge. You're not going to find the roots. Even if you calculate the error, you are calculating the error for x, and also you are calculating the error for y. The error is going to be really increasing. So in this way here, this way of rearrangement, it doesn't consider good. So what we need to do in here now, is we need to try to rearrange based on different x and different y. So let's try make our arrangement something like this. Okay, so that's mean I'm going to rearrange based on this x squared, and I'm going to rearrange based on y squared. So I'm going to get these two equations. And I'm going to start from scratch with the initial value of x is equal to 1.5 and y is equal to 3.5. Okay. So when x is equal to 1.5, y is equal to 1.5, what's the value of xi plus 1 is going to be?
2.7.
2.7. Perfect. So the value of y is going to be
2.86.
perfect. Okay. Now when you are looking at the values, 1.5, now it's 2.17, 3.5, 2.8. Okay, the numbers looks great. We iterate one more time. So let's go for the second iterations. The answer is going to be 1.9, and the answer here is going to be equal to 3. Actually, it's the true value for these two equations to be equal to 0 that supposed to be x it's equal to and y it's equal to 3. This is the two values that will make these two equations is equal to 0. So now when we are looking at our values in here, x is 1.9 and y is equal to 3.04. If you calculate the error for x and calculate the error for y for these two columns, you are going to see that it's the errors start to be reduced. So this is the way of rearrangement that it's guaranteed it's going to be converged, okay, towards the true value. Okay, this is the way of how to solve the nonlinear using the fixed point iterations. The second method is the Newton-Raphson. So before I move to the Newton-Raphson, do you have any questions about fixed point iteration to solve the nonlinear equation? Any?
Okay, sir. No problem so
Okay.
far.
Let's move to the last method for today. So the Newton-Raphson method. And since here we are solving the Newton-Raphson for two equations, so we are going to be using for the Taylor series expansion function for more than one variable because we are having x and y. So we are using more than one variable. So we are going to use the Taylor series expansions to get the equations of the Newton-Raphsons. So the roots of the equations will be occur when the value of x and y, they will going to be equal to 0. Okay. No worries about how to derive. Again, as it said, it's all the equation is going to be given at the end. So the equation of the Newton-Raphson to get the answer of xi plus 1 and xi plus and yi plus 1 is these two equations. This is the first equation, and this is the second equation. This is to find for x, and this is to find for y. The good things about these two equations in here for the Newton-Raphson method is the determinant is using the Jacobian system, and they are the same. So the determinant here is exactly the same determinant in here. Okay, so you can make this calculation for single iteration at one time only. How to solve, or I know the equation looks big and complicated, but actually it's not. The determinant is based on the Jacobian of the system. Let's see how we solve it. I think if we are going to run the example, it's going to be clear how to solve. So we need to use the multiple equations for the Newton-Raphson method to determine the roots of the initial guesses value of x 1.5 and 3.5. So Remember, we said that it's the true value of this example is x is equal to and y is equal to 3. Let me show you the example. Okay. Okay, our initial values, x and y, it's 1.5 and 3.5. Those values you didn't see it yet. And also those values you didn't see them yet. Okay, so this is the initial values. The first things that we need to do to solve for the Newton-Raphson for the nonlinear equations, you can see that here we are using the partial derivatives, okay, to find or to evaluate the initial guesses. So I need to get all these partial derivatives and I need to put them into their locations to calculate for x and also put them in their locations to calculate for y. So how actually I'm going to get these partial derivatives? Using my initial value of x and y in here. So x is equal to 1.5 and y is equal to 3.5. So first I need to find the partial derivative for the first equation. So the partial derivative for the first equation I need to get here is the partial derivative for the first equation for x. So we are going to look for all the values of x, then I'm making partial derivative. So here there's an x partial derivative, so it's going to be 2x. So it's 2x in here. Plus partial derivative for x in here, x will be gone because it's going to be 1. 1 plus y, 1 times y. So 2x plus y. Okay. We are going to use the initial values of 1.5 and 3.5. So 2x, which is 2 times 1.5, plus the value of y, which is 3.5. So the answer is 6.5. Do you have any questions about how to do the partial derivative? I'm making partial derivative for the first function here. Any question?
No, sir.
No.
So now, the first function also, it has the variable y. So I need to also to make the partial derivative for the variable y. So you get this, the partial derivative for the variable y. Here I don't have y, so I'm not going to make any derivatives in here. Here I have the value of y. So if you are going to make the partial derivative for the y is going to be equal to 1. So at the end, this function is going to be equal to x. So x actually as an initial is equal to 1.5. So we're done for the first equation. We are going to repeat the same for the second equation. The partial derivative for the second equation for x, so it's going to be equal. Here I don't have x, so I'm not going to touch it. Here I have the value of x, so it's going to be equal to 3y squared. So 3y squared, that's mean 3 times 3.5 squared, so the answer is 36.75. Then again, the second equation we are making is a partial derivative for the y. So here I have y, partial derivative is going to be equal to 1 plus g with the times of 2 is going to be equal to 6. So 6xy. I put the initial values, so I get the answer of 32.5. So now I have all the partial derivatives that I can put inside this equation to get the value of xi plus 1. Okay. So first I need to calculate the determinant. So the determinant is going to be based on the Jacobian of the first iteration. So that means it's going to be 6.5 times 32.5 minus 1.5 times 36.75. It's just Jacobian. So it's 6.5 times 32.5 minus 1.5 times 36.75. So I can find here is my determinant. The determinant will be equal to 156,125. Okay. Then we are going to calculate for the value of the function u and the function v. If I put the initial value, because here you can see I need to get the answer of the function u and the function of the function v. So what I need to do, I will use 1.5 and 3.5 inside my function. So x squared, 1.5x squared plus 1.5 times 3.5 minus 10 is going to be equal to negative 2.5. For the v0, so I'm going to use y, which is 3.5 plus 3 times 1.5 times 3.5 squared minus 57. So the answer is 1.65. So now I have all those values. I have all the values now, these values and these, to put it inside the value of the equation of xi plus 1 to get the new value of x I plus 1 and yi plus 1. Okay, you can see is from the first iteration is the answer is 2 and y is equal to 0.8. The next iterations you are going to find is that xi plus 1 is 2 and 3, which is equal to the true value. Okay. The way I'm explaining, the way I'm showing you my Excel file, things just looks easy. If you didn't try the example or didn't try the exercise, you are going to forget about these methods. So it's better for you to try. I'm going to give you about 5 minutes just only to get the same exact values from this example. Or you can look at this example from the textbook. You're going to find it. But I want you to try it now. Just only to get the same exact value of xi plus 1 and yi plus 1. If you have any questions, please ask. Okay, just try. Try to get all those values. Use a piece of paper and try to get the final answer of x is equal to 0.03 and y is equal to 2.84. If you get those, that means you already know how the method is works. This is the last thing for today. If you have any questions, please do ask. I'll give you 5 minutes to try the example. Any question about the example?
No question.
Okay, so I can see from here today we are not taking any new methods. We're just only using the open methods, which is fixed point and Newton-Raphsons to help us to solve for the nonlinear equations. So I hope that you understand the examples and the exercise. Okay, by the way, there is an exercise at the end of these slides. If you can make it, and you can check your answer later with me. So I need to determine the roots of the following simultaneous equation using fixed point iteration and the Newton-Raphson methods. So these are the two equations, and you need to employ the initial value of x and y is equal to 1.2. So you need to iterate until the approximate error is less than 0.05. With this error, you can do it till less than 0.05 using the fixed point. You can achieve that, but using the Newton-Raphson, the steps is going to be really huge because you need to iterate about 5 times using the Newton-Raphson methods to achieve that answer. Okay. Good news is if you are reviewing back the previous semester's answer or questions, you are not going to find questions coming at the midterms or at the final using the Newton-Raphson methods to solve for the nonlinear equations because the steps is really taking much time. So mostly we are avoiding that type of questions to come into exam. But maybe some of the lectures they are going to use it for assignment. I'm not sure about that. So just only you understand it. This is really good. So, but for midterm or finals to face this type of questions, I don't think so you can find. Okay, so for the exercise, you need to make the fixed point iterations till the error less than 0.05. But for the Newton-Raphson, you just make one iteration or 2 iteration. It's enough. So if you have any questions, please do ask. If not, so this is the last thing for our. So before you leave, please write your name and group. So today it's the group. It's really important because you are 2 groups together. If you have any questions, ask. If not, thank you very much. See you inshallah for the lab session. There's one group in here. Your lab is going to be on Thursday.
Class E.
Okay, so since Thursday is what you call it is a chuti, so I think your lab, I'm not going to replace it. Maybe I'm going to combine it with the week after. Okay.
Is
Okay, so that's all for today. Thank you very much for coming.